Okay, number 6 on the McGehee problem set. So we have a mass on a spring. The oscillation is horizontal, which I think is easier than vertical. So we have a horizontal oscillation, and we're told that the surface is frictionless. So if the surface is frictionless, what's the only force that does work on this mass, on this 1 kilogram mass? What's the only force that does work on it? Is gravity doing work on the mass here? Why is gravity not doing work? Because the force of gravity happens to be perpendicular to the motion. Forces perpendicular to the motion do no work. Is the normal force on this mass doing work on the object? No, because the normal force is perpendicular to the motion. What's the only force that does work? The force of the spring. So it's a conservative situation. If the only forces that do work are gravity or spring, then that means the mechanical energy of the object is going to stay constant. So before we start the problem, let's just identify our mechanical energies. So we know that it's oscillating 0.2 meters on both sides of the equilibrium position. So let's identify what energies we have. What energy do we have at this point over here? At this point, it's all potential of spring. Why no kinetic? Because it stops. Okay, what type of energy do we have at this midpoint right here, which is referred to as the equilibrium position? This middle point right here is the equilibrium. What energy do we have there? All kinetic. Why no potential? Because the spring is not stretched and it's not compressed. Okay, over here, it's back to potential of spring. Now, assuming no friction, which we can because the problem says to, all of these circles are equal to each other. The energy here and here and here is the same. The mechanical energy remains constant. Now, if friction were present, would that be true? No, because if friction were present, as the mass oscillated back and forth, it'd be losing mechanical energy, and eventually it would stop. Okay? All right. Part A, question A. What is the total mechanical energy for this spring box system? At what point can we find the total mechanical energy? Well, there happens to be 2 points. We could find the total mechanical energy here, and we could find it there, and those answers are going to be the same. Why could we not find the total mechanical energy by focusing at this point? What do we not have? The velocity. We're missing the velocity. So let's use this point right here to get the total mechanical energy. We're going to use the point where the spring is all the way compressed. Right here is the point we're going to use. So to do part A, we're going to go potential energy of spring, because the mechanical energy at this point over here, the mechanical energy is 100% potential of spring. So the potential of spring is going to be 1/2 kx squared. So it's going to be 1/2 100 newtons per meter, because that's a given right here, times x, which is 0.2 meters. That also was a given. And then this comes out to be exactly 2 joules. Okay? All right, question B. What is the maximum speed of the box? Now, in order to answer this, you have to know the point that has the maximum speed. Where will the box have maximum speed? Is the maximum speed going to be over here? No. Is it going to be over here? No. It's going to be at the point that has all kinetic, which is going to be right here. Now look, how are we going to go about finding the velocity at that point? Well, keep in mind, guys, what was the mechanical energy over here? Potential of spring. What was that equal to? 2 joules. So guys, guess what the kinetic's going to be equal to? 2 joules. What's this potential of spring over here going to be equal to? 2 joules. If there's no friction, the mechanical energy stays constant. Okay, so to answer this, we're just going to go, okay, the kinetic energy, that must be equal to 2 joules. So we go 2 joules is going to equal the kinetic, right, at this point right here. So we go 2 joules equals 1/2 mv squared. So the velocity is going to be square root 2 times 2 joules divided by the mass, which is 1. The mass is 1 kilogram, and this comes out to be 2 meters per second. So the maximum velocity is at the equilibrium position. Okay, third question, part C. What is the force of the spring on the box when the spring is stretched 0.12 meters to the right of the equilibrium position? So we'll erase this. Okay, so the box is now over here. Now look, which way is the force of the spring going to be when the box is pulled, when the box is to the right of the equilibrium position? I shouldn't say pulled, nothing's pulling it. Which way is the force when the box is to the right of the equilibrium? The force of the spring over here, the force of the spring is going to be to the left. Now look, to the right is plus, to the left is minus. This is our sign convention. So what's the equation? What's the equation for force of spring? Force of spring is equal to K times displacement, Kx. And technically it's negative. You'll notice that on the equation sheet. Now why is it negative? It's negative simply because force of spring is always opposite x. It's always opposite the displacement. So let's plug into this. So it's going to be negative 100 Newton per meter. And then what was the delta x here? How far off the equilibrium? 0.12 meters. The meters cancel, and we get negative 12. Now, guys, why does it make sense the answer is negative? Look, so which way was the delta x? The delta x was to the right, right? The delta x was to the right. Which way is the force? To the left. The force points to the left, which is negative. Okay, question D. Oh, wait, hold on. All right, question D. We are now focusing on a point that's midway between the amplitude and the equilibrium position. So question D focuses on this point. Hold on, let me clean this up some more. So we're focusing at 0.1 meters to the right of the equilibrium when the spring is stretched. So we're focusing like right in here. Now at this point right here, what type of energy is the mass going to have? Or what type of energy will the system have? Will we have kinetic? Yeah. How do I know we're going to have kinetic? Because the box is moving, and we're also going to have potential of spring. How do I know that? Because the spring is stretched. So there's energy in it. Now look, what is this total energy going to be equal to? 2 joules. How do I know that? Because look, what were these energies all equal to? 2 joules. Mechanical energy stays constant. So that means the mechanical energy at the midway between the equilibrium and the amplitude, it's still going to be 2 joules. So here's how you solve part D. You go, okay, our 2 joules of mechanical energy is now going to be in the form of kinetic and potential of spring. So you go 2 joules, now you plug in the equation. 1/2 mv squared. Potential of spring is 1/2 kx squared. So this comes out to be 0.5, right? So k is 100, x is 0.1. Uh-oh. Okay, hold on, let me just finish this. So we end up getting 1/2 mv squared equals 1.5 joules, and then solve for velocity, and you're going to get 1.73 meter per second. And then, guys, part E is the same thing, same exact thing, only now we're over here.